Hello, my name is Mr. McQuire. I want to give you a warm welcome to this session on forces. It's session number 4 entitled Forces and Elasticity. So before we start, let's try and find somewhere quiet and free from distractions to work, and you will need a pen and paper, and if you have access to a calculator, you may need a calculator as well for calculations later in the lesson. So let's look at our learning outcomes for today. First of all, the challenge is to describe what happens to elastic objects when they are stretched, to represent this on graphs and state whether or not materials obey Hooke's law. And I'll aspire to discuss the extent to which a material obeys Hooke's law and calculate the spring constant. Now this could be done from a graph, and today we're not going to focus on the graph work that this session requires. That'll come in a future presentation. So for our starter today, we are going to look at the following picture, and I'd like you to think of a number of ways that you could deform the objects that are in front of you. They look like marshmallow sweets to me. And I'd like to think of words that you could use and actions you could use to describe what it is that you have done to deform those sweets. You've got a minute to think of those words. Okay, so let's have a think about the words that you've come up with. Hopefully in the last minute you've come up with things like squash and stretch, maybe tear. These are all descriptors of things that we can do to objects using forces, and we're going to use that knowledge and apply it during the course of today's presentation. So we're going to start producing some notes now in today's lesson. I'd like to put the title of Forces and Elasticity, and we're going to just look at this briefly before you put it down. When a force is applied to an object, three things could happen. Number one, which is in bold, which is what we're currently looking at in today's presentation. Number two, the speed of an object changes. And number three, the direction the object is traveling in could change. And they're all implications of forces on an object. So you've got 2 minutes, please, to write down the title and those 3 points that we have there. Okay, so let's have a look in more detail at point number 1 that we've just made then. So the shape and size of the object changes, and we can list the number of ways that we can deform this. First of all, this may be a new word to you, but the word that we would use as stretch is called tension in science. Compression we may well use in something like a bandage, for example, where you have a joint injury. And shear is another word that we would use for kind of twist and torn. So elastic behavior. If a material returns to its original size and shape when you remove the forces stretching or deforming it, we say it is showing elasticity. Inelastic behavior, if the material stays deformed after you have taken the forces away, then we say it is inelastic. And if you apply too big a force, even an elastic material eventually will lose its elasticity. Now, the information that we have in front of us can be put as bullet points. So first of all, I'd like you on one line just to write down some words that we can use with some arrows to show what tension, compression and shear means. They're very simple diagrams and they will help revision in the future. And then we need to understand what elastic and inelastic behavior means. Now, those sentences are quite long, but I'm sure that you could shorten those very much if you tried and read them properly. So elastic behavior returns to its original size and shape. Inelastic behavior, it stays deformed. Even an elastic material eventually will lose its elasticity. Now, the information that we have in front of us can be put as bullet points. So first of all, I'd like you on one line just to write down some words that we can use with some arrows to show what tension, compression and shear means. A very simple diagram, and they will help revision in the future. And then we need to understand what elastic and inelastic behavior means. Now, those sentences are quite long, but I'm sure that you could shorten those very much if you tried and read them properly. So elastic behavior returns to its original size and shape. Inelastic behavior, it stays deformed. So I've already helped you with those. So you've got 2 minutes just to define the word tension, compression and shear with little diagrams, and then just to write some very brief things down about elastic behavior and inelastic and what they mean. Okay, so in your notes we've defined what forces can do to objects, and then specifically looking at elastic changer, we've talked about elastic behavior and inelastic behavior, and just improve the quality of our vocabulary as far as the use of the word tension, compression and shear. So let's see if we can apply those now through the rest of the presentation. So we're going to bring some words together. First of all, I'd like you to do a little bit of thinking. On the right hand side we've got a bungee jumper as a cartoon picture with a piece of elastic around their legs. You need to describe the energy changes which could occur during a bungee jump. Now this is a skill that you all may already have in terms of being able to draw an energy transfer. So when the bungee jumper is stood at the top of the tower, what energy does that particular bungee jumper store? Then we would put an arrow, and then we would write down the name of the energy that we would transfer that into. And then we would put another arrow and so on, and just discuss for a second as you write it down with arrows in between what energy changes take place as somebody jumps off a tower to do a bungee jump. So you have got 1 minute to try and write down your list with arrows in between, and then I will reveal under the blue box what we think is happening. Okay, now each of the boxes under here represent an arrow. Let me say that quickly to you now. So gravitational energy at the start from the person stood on the tower, and then an arrow moving to kinetic energy, which is energy due to movement. That then is changed as the person reaches the bottom and the elastic starts to stretch and slow the person down. We end up with elastic potential energy. We then have another arrow because the person now is being pulled back up again by that elastic, which means it's movement energy. As the person goes higher and higher, they are adding gravitational potential energy. And so on, because we're back at the beginning of those. And that obviously will take place and continue for quite a long period of time before all the energy that was stored in the gravitational potential energy at the beginning is lost to the surroundings as heat. So here's our principal point to remember from the bungee jumper, which is when an object is stretched, it stores elastic potential energy. Now, if you don't know that, then what I would like you to do is to pause the presentation now and to write that sentence down, which is really important for the rest of the presentation today. Okay, there is in front of you a graph, but basically it is in a diagrammatic form, in the form of a diagram, but I'm going to show you what that would look like as a graph afterwards. First of all, we have a spring with no loading at all on the left hand side, so that is unstretched, and then we have an extension of that which takes place because we have put one weight on the bottom. We then have a further extension from the original unstretched, increasing each time. What I'd like you to do now is just to think for a second about the observations you would make of the experiment left to describe the relationship there is between the extension of the spring and the weights that are applied. I'd like to challenge you to not just think the obvious, which is the more weight you add, the bigger the extension. I'd like you to look a little bit harder than that, because it's a little bit more detailed than that, and I really want to give you the basics so that that one's out of the way and you can think a little harder about the extension that has occurred. You've got a minute to look at the diagram and see if you can come to any deeper conclusions. Okay, this is a good moment before we discuss what's shown in that diagram to look at the keywords at the bottom of the page. We've already talked about a substance that is elastic and inelastic. Inelastic was something that was permanently deformed. We're going to talk about Hooke's law, and that will come up as part of our calculations as well today, and elastic limit. And then we have this expression here, directly proportional. We're going to be using that now as a mathematical term. If you look at the extension with one weight added, and then look at the extension with 2 weights added, and then in your mind just double that and look at the extension with 4 weights added, hopefully you will begin to see some kind of relationship. Now I'm going to move on to the next slide and a graph version of this picture. So this is far more helpful than the previous diagram was. Let's see if we can use it better. So first of all, the extension with 1 force applied was just over 0.1 meters here. When that's doubled to 2 forces applied, that then is on 2.2-ish. Now if we then jump to 4, you can see that that then has jumped to around 4.8. So what I'm trying to get across to you is that there is a deeper relationship than more force applied equals greater extension. What we are looking at here is a spring relationship with the force that is directly proportional. And what that means is if you double the force applied, then you double the extension that results from that. And that's what that graph is showing. So let's just get that word directly proportional into our minds, because it's an important relationship that we would need to recall. So let's reshape the way that we think for a second and just develop the best practice that we can use in our discussions in an exam. So first of all, as the mass increases, the extension increases. I gave you that because I didn't want that to be your only thought. So let's say that better. As the force applied to the spring increases, the extension increases. Okay, that's just a better way of using our science vocabulary to do that. So Hooke's law relates force and extension. So getting it into the habit of using force will help later. So let's try another one. There is a positive correlation. In other words, one increases, the other increases. Well, let's improve that sentence. The extension is directly proportional to the force applied. Why is that better? Because it's much more detailed. Directly proportional tells us that the relationship is linear and that the line passes through the origin. So when there's no force, there is no extension, and then we have this directly proportional relationship, which means that every time we double the force, we double the extension to a point, and we'll come back to that in the future on this presentation. There is a good correlation. What that means is the data is reliable as all the points lie close to the line of best fit. And the reason that's better is, again, because it involves a lot more detail in our answer. So let's try and communicate in a detailed scientific way and just develop our language for communication with other people when we look at these graphs. Okay, let's now look at one of our other keywords from the bottom of the page. On your paper, I'd like you to put the title of Hooke's Law. Hooke's law states that the extension of an elastic substance or material is directly proportional to the force applied. Then we have this equation. I don't want you to be concerned about that other than to write it down. Capital F equals capital K small e. And it's important that we write that clearly, so give it its own line, don't bunch it up. And then, as importantly, we need to understand what each of those words means and what the units are that we would use. So first of all, we have F equals force measured in newtons. E is the extension measured in meters. Notice the spelling of the word meters. And K is the spring constant measured in newtons per meter. So I'd like to spend 2 minutes now and write those down as part of your notes very accurately for today's presentation. Okay, hopefully you've completed those. If you need more time, obviously, just pause the presentation now. Now let's just run through each of those letters for a second. First of all, next to the word newtons, could you write a capital N, which is the unit we would use. The extension in meters, just put a small m, not a capital M. And then finally for K, newtons per meter, is then N /M. If you could write those next to those, we'll use those abbreviations. as we go into our calculation. So we're now going to start applying the equation that you have written down. It's important that you learn to recognize the various parts of a question so that you can insert the information and data into the correct part in the correct format. So what you've got in front of you at the top of the page here is a list of things that you need to do for each of the two questions here. First thing you should always do is write down the equation that you need, and that's the one that you've already written in your notes. Secondly, you then need to look through the question to check that the data is in the correct format in units. So for example, in question 1, I will tell you for absolutely nothing that the extension should be in meters, not in centimeters, and you will need to show your skills in converting that to the correct units to put into the equation. You then need to rearrange that to provide you with the answer, whatever letter it asks for in the question. For example, calculate the spring constant is the important part of this question. And then finally, you need to calculate an answer for this, which includes the correct unit for this particular question. So what I would like to do is to give you a minute on each of these questions. I would then like to cut to a clip where I can go through how to answer the questions correctly and just make sure that you are going through the stages properly. So try your hardest for 1 minute on each question. Okay, now let's spend a few minutes just looking through the answers and how to do those properly. Okay, let's have a look at the questions. We'll start with question number 1, and I'm going to follow the principles that I have put in the slide at the top. So question number 1, first of all, we are going to write down the equation. Force equals spring constant times extension. Then I'm going to write down those letters next to it, and I'm now going to look at the question and make sure that I get them the numbers into those into the formula in the correct format. So first of all, from the question, the force is 1.5 newtons. That's straightforward. I'm asked to calculate the spring constant, so we don't know that. Then the extension, I'm given in the question 45 centimeters at the end and 15 centimeters at the start. So my first issue is the calculation of the extension. So I need to work that out, which is 30 centimeters. Now my next issue is converting that into meters. There are 100 centimeters in a meter. So I'm going to convert that by dividing by a 100 to find that share of 100 centimeters, which means that I have 0.3 meters for my question. So I now have the correct format for all of the parts of the equation. I'm now going to insert those into the equation. So a 1.5, that's F, equals K, which I don't know. I'm just going to put K in there, times 0.3. Okay, now I need to rearrange the equation so that I end up with K equals. So let's look at that for a second. First of all, K is being multiplied by 0.3. I need to remove 0.3 from this side, and the rule in maths would be whatever I do to one side, I must do to the other. So therefore, I am going to divide both sides by 0.3. 0.3 divided by 0.3 is 1. 1.5 divided by 0.3 gives me an answer of 5. So in summary, K equals 5, and the units, then making sure that we put those in because it is spring constant, is newtons per meter. So that's question number 1. Now let's have a look at question number 2. Okay, exactly the same principle, but a little easier this time. First of all, for a mark, we put the equation down, F equals KE. Now I'm going to write my letters down, force, spring constant, and extension. And now going to interrogate or look in the question for those. This time it's asking me for force, so I don't know that one. The spring constant is 30 newtons per meter, and the extension this time is 0.2 meters, which is given in the correct way for me this time. I don't need to convert anything because it's in meters. So let's put some numbers in. F, which I don't know this time, equals 30 times 0.2. Okay, if I need a calculator, I'll just stick that into a calculator, and the answer is 6 newtons. Every time we follow exactly the same protocol. The equation, get the numbers in the correct format, insert them into the equation, then rearrange the equation. In this case is in the right order already. Put the numbers in a calculator. If we need to be secure with those, then get the correct answer. So now let's take our data and turn it into graphs for a moment and just see what mistakes we can make in looking at these particular graphs so that we avoid them. So on the left hand side of the graph, the y to the sky axis, we have the extension, and then on the x-axis we have the force. Now in this particular graph here we have an issue. I'd like to think for a second about what the issue is that could go with this particular graph and what has occurred so that they can be avoided in the future. And then when you've thought about that one for a moment, something strange is happening here. We have a linear straight line here going through the origin, and then all of a sudden it starts to curve and change shape. And the question that we are asking is what issues you can see with the graph, and to see if you can work out what caused them and how they could be avoided. I'm going to run through those with you in a moment, so just have a think. Okay, so let's look at this first graph and discover what it is that's wrong. Maybe you were thinking this. The student plotted the original length instead of the extension. So let me just give you some numbers for a second. If we had a spring that was not extended at all and we measured the length of it as 10 centimeters, then that is the original length. But we need to remove that from our calculations because the only thing we're plotting is E, or the extension. If I added then a mass to that particular spring and it stretched by 5 centimeters further, then we need to remember to remove the original length of the spring from each of the plots. So that is why the y-intercept down at the bottom here doesn't start from 0, because this particular extension here represents the length of the spring. The spring constant would still be correct because the gradient of the line would be the same, but they have not shown the directly proportional relationship that we would expect because of that mistake. So let's be careful, because this is required practical. We need to make sure that we do that. Let's keep moving. So the issue with this one is not more complicated. It's just an interesting point that everybody has experienced when they have at some point got hold of an elastic band to flick at somebody and they pulled it so hard that it snapped on them. So this student has increased the force to the point where the elastic limit has been exceeded. So we have here working within the limits of elasticity following Hooke's law, directly proportional, but then at this point beyond where the pointer is currently showing, it then starts to not follow that, and the spring is going to be permanently damaged or break in the case of an elastic band, for example. It won't go back to the original length. If they use numbers from this graph, they must limit it to the linear section. So if you wanted to calculate the spring constant, for example, you would only be able to use the straight line section of the graph. Okay, so here is our last major piece of work for today's presentation. Now, there will be a point where you will need to carry out the required practical and watch maybe YouTube clips to show how it's carried out in more detail. But these are a list of instructions or directions that we would write down to describe how to do that. I want to start with the diagram on the right hand side. So the first bullet point or tick that's on here says a description of the equipment shown in the diagram. I think the diagram saves an awful lot of work, so what I would like you to do, because you'll need to put this list down, is to draw the diagram instead of describing. But you will need to label the diagram appropriately. First of all, we have a ruler, and the ruler is used to measure the extension. This here is the spring, and then we have these masses that are on the bottom here that are slotted masses where we can add very easily more force to the diagram. We have a clamp which is here. We have the stand, which you'll be used to seeing in science, and then we have this turny thing here called the boss, which helps to control, and that is holding the ruler with the spring suspended off it. So the purpose of the investigation is to add masses and just to measure the extension. So that diagram covers all of what I've just said. So let's move on to the second bullet point. So I draw the diagram for the first. We're then going to apply a range of forces to the material, which in this case is the spring, by adding different masses. We're going to measure the extension for each force, and what that means is the difference between the original length and the new length, and we're going to do that using this complicated measuring device called a ruler. Please make sure that you state that in your method. We're then going to plot a graph of y-axis extension against x-axis force, as we've seen on previous graphs. And finally, we will read the values from the graph, which will enable us to calculate the spring constant, which is F divided by E. Now, that's one of our outcomes on the Aspire. So the spring constant equals the force divided by the extension, but we have to convert those into meters to do that properly. So what I would like to do now is not to set a timer for you to put the diagram and this particular method down. I'm going to pause this for maybe 10 seconds. I'd like you then to pause your presentation and to take as much time as you need at this point to enable you to put this method down with a diagram. The title is at the top of the page, Hooke's Law Required Practical. Okay, so you should now have a completed diagram and method for the Hooke's Law Required Practical. If you haven't done that, please make sure that you do, because that will be coming up again in a later presentation, which is only on the Required Practical, and that will save time from having to copy it out then. So here's our plenary. I've got the diagram that we've seen slightly earlier with extension plotted against force, and the question I'm asking for revision: does this material obey Hooke's law? Now, I've given you a choice of answers for this, and the choice is yes or no, but in this case I've also given you a choice of in part. So looking at that graph, does this obey Hooke's law? Is the answer for you yes, no, or in part? Now, the answer is not straightforward. So the answer is, for the part of the graph that is straight, yes. But then beyond that point, the answer is no, because we've exceeded the elastic limit of the material we're using. So the correct answer then would be in part, because we've got a bit of yes and we've got a bit of no. So I would go with in part for that. Okay, what is the equation that links force, extension and the spring constant? Now we need to know this equation. So just recall it, look at your notes, shout it out. And the answer is F equals KE. And I've written it down there with some detail, or force in newtons equals spring constant, which is newtons per meter, times the extension, which is measured in meters. So we'll finish by just looking through our learning outcomes for today. First of all, for the challenge, we have described what happens to elastic objects when they are stretched. We've represented it on graphs or seen that happen. We stated whether or not the materials obey Hooke's law, which should be a linear or straight line. And then for the Aspire, we've discussed the extent to which materials obey Hooke's law, and we have seen how to calculate the spring constant. Thank you and goodbye.